Hi, Bob Ruckle here from Siltech Corporation. I'd like to present to you today a paper on bioorganic silicone additives. We're presenting this at the Waterborne Symposium in late February 2022. So this is a run-through, if you will. Right, thanks. Okay, so the title is Bioorganic Silicone Additives. These are non-petroleum based alternatives to some existing raw materials. My colleagues Tom Chung and Yanyun Lo did all of the lab work, and I always appreciate their efforts. Our contact information is down there. It's easy enough to figure out our emails. Mine is robert@siltech.com, and Tom is tom2@siltech.com. There's the phone number there as well. So the reason we're doing this work is there are two drivers. There's a very strong market trend in the sort of coming up post-COVID era for plant-based rather than petroleum-based components. This trend has always been there, but it's been dramatically accelerated by the pandemic. The other possible driver this can actually address is an alternate supply chain. There are a lot of supply problems today. Silicones are hit as well as everything else. So there's two things that we can address with this. So first, let's talk about why you use silicone additives. They're really very unique materials, very desirable. These are some of the properties of just pure silicone oil. They're stable to free radicals, so that means oxygen and sunlight stability. And the third bullet, high thermal stability, also comes from that. They're insulative against both electrical and thermal pressures. They give low surface tension, which gives you spreading and wetting, and they have very minimal interfacial tension, so they help stabilize foams or even destabilize foams. They also have a very low coefficient of friction, so they're great at providing slip and protection against certain things, so anti-graffiti or other assaults on the surface. They're low T sub G materials, 153 degree Kelvin, which is a minus 120 degrees C for those of you who don't think in Kelvin terms. So these are pretty much always liquids. They're low odor and toxicity. There's a lot that's been studied about these materials. Very little toxicity has been found. Most of that, according to the toxicologists, are specific to the rats that they were tested on. They're also water repellent. That makes them great for fabric treatments. They're gas permeable, which is why they're used in contact lenses, and they're incompatible with most things. So they're not soluble in water, they're not even soluble in most oils. This is a property that we really typically want to change. So to remedy that, we react this with an organic material, just to make it a little more organic soluble, a little more miscible. When we do that, that does affect these other properties that are desirable, but typically what you get is something in between, sort of a hybrid molecule. There are two different modifications that are commonly done in coatings. One is shown here. It's an aliphatic hydrocarbon. Aromatic hydrocarbons are used occasionally, but by far more common is aliphatic. These can be anywhere from ethyl to C32. You can see there are 3 degrees of freedom there, X, Y, and M. I should be using this, X, Y, and M. These will affect molecular weight percent silicone, and the nature of the properties. Additionally, there's some proprietary treatments that can be done. In particular, these are often solids. They're often waxes if you get M up high enough. So we'll often prill those just to make them easier to use. The other, and probably more common in coatings, although the hydrocarbons are common enough, but the other modification that's done is silicone polyethers. So here we've attached a polyether, which I'm showing polyethylene oxide. Polypropylene oxide can be used as well. The main reason to use that is if M gets above 15, this will start to become waxy. And by putting in the propylene oxide, you lower the crystallinity and keep it a liquid. By varying these properties, by varying these variables, you can affect properties. So a greater value of X over Y will make it more like silicone, because we put more of the unmodified silicon atoms in there. More Y will make it more like the hydrocarbon feature. This is often called a capping group on the polyether. These are typically hydrogen methyl or acetyl, occasionally butyl. The hydrogen material is the simplest. It tends to give you more water solubility, a little more foaming, and it can be reactive. There are three different architectures commonly used in coating. The one here in the upper right is called a comb or pendant structure. And here we have some unmodified silicon atoms and some subunits that have been modified with the hydrocarbon chain or polyether chain. Less common, but still pretty often used, is the linear version where we've modified the ends of the molecules. And here these tend to give you, they lay at the interface much more efficiently, so they give you better slip and better protective features. So these are often used for slip coating, for COF reduction, or for protection, anti-graffiti maybe. And then the final modification, this is often referred to as a trisiloxane because there's 1, 2, 3 silicons. This is actually distilled to give you a monodispersed trisiloxane. Quite important. These are often used as the super wetters or super spreaders. Before I really talk about what we want to talk about today, I do want to mention that in the past, Siltech have actually offered a castor oil modified silicone, which is a sustainable plant-derived material. We made these primarily for personal care, so they're not on Tosca. We never put them on Tosca. We did look at them in coatings. They tend to give slip and mar resistance, all the properties that you expect, but we never did get anything that gave us really great flow and leveling. This work was done 10 or 12 years ago when the driver for sustainability was nowhere near as loud as it is today. So we didn't really push that, but these materials are available. And just a quick sense of the data. Here we've got some properties across the top. 1.75% of the castor oil derivatives were added to a coating system. It's a UV cured system. With 3 different castor oil derivatives and the control at the bottom. There was a minimal impact on gloss, and coefficient of friction went down really to a quite reasonable 0.4 and 0.3 numbers. But over here you'll see the surface appearance. We had orange peels and even a little bit of waviness. The control had craters, but the key point is we didn't improve the flow and leveling, which is one of the main reasons you use silicone additives. We didn't really push these materials. And just one last aside before we talk about today's efforts. How are silicones made from silicon? So here in the upper left, we just have a representation of the silicon element. This is very prevalent in the Earth's crust. Between silicon and oxygen, they account for almost 3/4 of the elements, mostly in the form of silicon dioxide. So this is purified to be silicon metal and then reacted with methanol and HCl with some catalysts. All of these ingredients are available from nature, if not always used from nature. Methanol is more typically taken from petroleum, but there are biochemical pathways for methanol. What you get out of this is chlorosilanes. These are very reactive materials, typically not sold other than to silicone companies or other industrial companies doing similar reactions. They're used in electronics and they're used in solar panels. These are then reacted with water and given a handful of intermediates that aren't represented here, but eventually get to silicone itself. Just want to point out this material is called silicone. It also has some other names: polydimethylsiloxane, PDMS, simethicone in the drug market, and dimethicone in the personal care industry. It's used really everywhere. It's considered to be very safe, among the most toxicologically studied and low toxicity polymers known. And what we do with this is we take some of these small pieces, and I sort of alluded to them here, that these small pieces are hexamethyl disiloxane, which is the end capper of the polymer, some unspecified silanic hydrogen. This is typically a long polymer with some end cappers in all silicon hydride units as subunits. And then some volatile silicones, or D4 is common, D5 can be used as well. Both are very common in the industry. And these are just redistributed with a little bit of acid catalyst to give you a polymer. And that polymer has some silicon hydride bonds that are quite reactive. This material is occasionally sold in the open market It's used in mold release, for example. But most typically, we would only sell this to a very sophisticated chemical company who knows how to handle it, because it can be quite dangerous. Silicon hydride will generate hydrogen gas. So that's reacted with a terminal olefin to generate under platinum catalyst. This terminal olefin is petroleum sourced, and this is what we're talking about today. That gives you now a modified silicon polymer where the hydrocarbon or polyether part is appended on there. I've only shown the kiln structures. I didn't show the other architectures. But what we'd like to do today is talk about what if we made this from a biosourced material. And there is some source that's come on the market, so we're able to do that. By doing that, you've made a significant portion of this molecule bio-based instead of petroleum-based. And just to give you an idea, that organic piece can be anywhere from about 30 to up to 80% of the weight of the molecular weight of the coatings additive. Just to talk about the synthesis of these petroleum pieces, they're ultimately derived from ethylene, which comes from the petroleum industry. Various catalysts are used to make the alpha olefins, or it can be reacted into just ethylene oxide. And then that's reacted with allyl alcohol to generate the allyl polyethers. What we're talking about today is to take ethanol that comes from sugarcane and use that to generate the ethylene, which is then plugged into the synthesis I just showed you. No one's commercially doing this to make the alpha olefin, so I didn't show that here, but there is a source available that makes the allyl-started polyethylene oxides. That's what we're talking about. So the hypothesis today is that these coatings additives, which are laboratory synthesized using bio-based organic components, they'll behave the same as the corresponding commercial petroleum feedstock sourced additives. So the testing to do this is 7 different pairs of structures. In the upper left, we have the comb structures. And so we've named these products to be C for comb or L for linear. 2 of them are the linear ones. And then they're either P for petroleum or B for bio-based. So in each of these 7 structures, we have both the petroleum and the bio-based materials. The first 2 structures have low values of X relative to Y. These tend to be wetting agents when you do that. They tend to be very soluble. So these materials are dispersible to soluble, and they're very good at wetting agents. These are something you would use for flow and leveling and coatings or to wet out the surface. And then C3 and C4 is a little bit higher. You've now increased X relative to Y, and so you get a more silicone-like material. These tend to be dispersible in water, and they might be used for a slip type application or protection if you want anti-graffiti or some other protection. And then the C5 material, it's got 8 of these and 4 of those. That's sort of the middle of the road. That gives you both good wetting and some slip, and that's commonly done in coatings, is to use materials like that. They're middle of the road structures, I think of them. And the last 2 materials are the linears. And here we just have, this is the only value we used. We only used the 10EO chain, and we varied that 10 and 25. I didn't actually say this, but what's commercially available is 8EOs and 10EOs bio-based. So all of the products we're talking about will be one of those 2 options. So first, let's have a look at the physical properties. I'm showing down the left side these 7 pairs of structures, petroleum and bio in each case. Across the top, viscosity, and then our lot history, because these are commercial products. So we have the viscosity history with the standard deviation, and then the second line is our specification range. And then the third column is surface tension. This is a 0.1% solution. We don't normally measure that for our commercial products, so there's no lot history, but we'll compare the 2 that are made. And then appearance. See as the appearance is the same in all of these. At the C1 pairing, there's a little bit higher viscosity for the bio-based material, but it is almost within 1 standard deviation and well within specification. The surface tensions are really very close. The point I'm going to make here over and over again and we see this with these bio-based materials, is there's a little bit of bias with the samples we have. They tend to be more viscous. They tend to give you higher surface tension. And what we think is going on is the distribution of the polyether is slightly different. There's a little more EO, a little more higher average molecular weight. So these two suppliers are using slightly different processes perhaps, but they're well within tolerance. So the second structure is actually the one that's furthest out of whack. We go from 103 to 170 on viscosity. That 170 is technically outside of our specifications. So this one will be a little bit of a challenge. It's a low molecular weight. Surface tension is still pretty close, but this one is probably the furthest apart. And the C3 and C4, you can see they're really quite close, 220 to 250. That is well within specification. 300 to 340, again, well within specification. We didn't measure the surface tension here. It's just not soluble enough. The C5 material is almost identical. And then the linear materials 1 and 2 are again show this bias, where the bio-based material is perhaps a little bit higher molecular weight, but within specification. Just want to point out the surface tension. This is the data I just showed you, but graphed. In each case, the two red ones are C1, petroleum and bio-based, and then C2, petroleum and bio-based. The structures that have issues are the ones that are the least soluble, and this is where you have the greatest sensitivity to surface tension. So I think there are really very minor differences in the polyether that we're picking up in this very demanding test. Looking at foam height, and here we just take a large graduated cylinder, make a solution of the material. I believe it's 1%. It's not noted here. And then we sparge that with nitrogen, and it creates a foam. When we stop sparging, we start reading the measurements, the volume measurements from the side of the cylinder. So 0 minutes is the first reading, 1, 3, and 5 minutes. Just for simplicity, we'll look at 0 and 5. Also, we do comment on the appearance, and all of these you can see that the lab person, Yanyu, noted that they're the same in every case. They appear to be the same. And you see 165 to 155, 135. In all of these, you see really very close numbers. Even the materials that don't foam very much, they stay pretty close. The biggest one is actually the L1 here. This is the only one on the screen that uses the 10 EOs. So I think that 10 EOs is perhaps just a little more out of whack. And this is just plotting that same data. You can see the L1 structure is the one that's probably the most out of whack. Sorry, it's probably not clear. So the two green ones are petroleum and bio-based for the C1 structure, etc. So comparing these two, 1 and 2, 3 and 4, etc. You see this is the one that's really kind of out of whack. So we also did some evaluations in coating systems. First, we did 0.5% in a waterborne polyurethane dispersion. And it's important to note that the appearance, the flow and leveling, the foam generation are all very similar to all of these. Although some of the products we chose had poor flow and leveling, it had it with both the petroleum and bio-based versions. Let me just show you that. For some reason, we have a picture of uncoated aluminum, but we also have, this is typical of all but one of the additives here. So they all gave really nice flow and leveling. The C4 additive did not give very good flow and leveling, but it looks the same for the C4 and this petroleum and bio-based. So since we're looking for differences between P and B, we're basically just seeing them behave the same. And just to perform a comparison here, the C2P and C2B, this is a composite photo that's the same drawdowns, just at different angles. You can see really they look identical. A very sensitive test can be coefficient of friction. So just from those panels that I just showed you, we're looking at no additive, and then C1 bio, and this is static and kinetic. The red bars, the kinetic coefficient of friction, tend to be much more sensitive. When you do coefficient of friction, the static ones there tends to be a tackiness to the coating. So once it starts moving, that's where you get the more accurate number. So what you see here is in the C1 structure, the blue bars are very close, the red ones are identical. The same thing in C2, C3, C5, L1, and L2. So all of these are really performing identically on coefficient of friction. Just doing the same thing in a UV clear coat, 0.5%. Same thing, they all appeared to be the same. We looked at these materials just to show you. And the same COF data, these really are identical, particularly the kinetic readings. So with that, we feel like we've proven our point. There is a little bias towards higher viscosity and higher aqueous surface tension with the biosource samples. We believe that's consistent with the polyether samples coming from different suppliers. So even though they both say ADOs, one is 7.8 and one is 8.1 maybe, there's a minor differences between the things. They're within lot-to-lot variation of our commercial histories, and we saw no significant differences in the appearance of the coatings or the properties that we could measure of the coatings. So we feel like we proved the point. These silicone polyether derivatives made from newly available biosourced EO chains compare very favorably to products made from traditional petrochemical sources. With that, thank you for your time listening here, and feel free to contact us if you have any interest. These products are available commercially. Thanks.